Welcome back to geometry. We want to continue taking a look at section 20 on circles. And what I'd like to start with is just returning back to theorem 20.6 here, the diameter chord theorem, the perpendicular diameter chord theorem, actually. I'd like to give you a nice little hint for the proof of this theorem. And what I'll do is I'll give you a nice image to consider. So in and of itself, just observing the theorem, we want to see that we have some circle with center O, of course, and we have a diameter AB. So let's say we have a diameter AB, starting to look like a Pokemon ball. And then we have a chord CD where it's perpendicular. So CD. So what the theorem says is that if we have a diameter and we have a chord that is not a diameter, then these are perpendicular if and only if AB bisects CD. And essentially what this amounts to is recognizing the distance from O to C and from O to D. That's what the proof relies on. So maybe even, let me get rid of these. This is an image of what the theorem is stating. To take it to the next level and say, consider this image in your proof, right? Just consider the distance from O to C and the distance from O to D and what you know about points on perpendicular bisectors. And that should help you out quite a bit as you work on that problem. All right. So let's move on to secant lines, secants and tangents. A secant line of a circle is a line that contains exactly 2 points of the circle. Well, that doesn't seem terribly strange. Don't all lines? Well, not quite. Of course, tangent lines contain exactly 1. So a secant line of a circle is a line that contains exactly 2 points, and a tangent line of a circle is a line that contains exactly 1 point. Excellent. So keep in mind here that the secant line is, right, so if we have some circle, a secant line is a line, continues forever, contains points outside the circle. Compare that to a chord, which is a line segment that only has lines, or that only contains points inside the circle. So a secant line compared to a chord. We want to recognize that difference there. All right. The tangent radius theorem. If T is a tangent to a circle, that means it only touches 1 point, right? As we see here, touches exactly 1 point. If T is tangent to the circle at P, then what must be true about OP and T? Well, they're actually perpendicular to one another. T is perpendicular to the line segment OP. And we'd like to take a quick take a look at a proof of this. There's a bit of room here, so certainly it's not going to be the shortest proof we've seen. But let me describe to you what we're going to do. We're going to go ahead and assume that they are not perpendicular to one another. And what that would give us is it would give us some other point where it is perpendicular. Of course, that looks a little bit funny because we know it's not perpendicular over there, but it's going to give us some other point. And then if we remember that points on the perpendicular bisector only lie on the perpendicular bisector when, right? So we of course need a perpendicular bisector here. That means we need some other point. Let's call it, we'll call it something else. So if we find this point to be the perpendicular through O, and then if we find this point the same distance away from here, so that way this is the midpoint, then the perpendicular bisector, right? A point lies on the perpendicular bisector if and only if it is equidistant from both of the endpoints. So this distance here and that distance there must be the same, which means that this point lies on the circle. And of course, that seems a little bit silly, and that's where we'll find our contradiction. So let's just start with this and work through this theorem. So first, T is tangent to the circle centered at O with radius OP. That's what's given, and it's tangent at P. Excellent. So the next step, let's suppose, for a contradiction, of course, that they are not perpendicular. So suppose that OP is not perpendicular to T, and we want to assume for a contradiction. All right. Let's move that over a little bit. We're going to need to label some stuff. All right. So what we want to do is we want to find the perpendicular to T that passes through O. So let's let QP be the line that is perpendicular to T, where, of course, Q is not equal to P. So we're saying that this is the point Q over here. Let's put that in red. And this is the perpendicular existence theorem. That gives us that point Q, or the perpendicular and that point Q. All right. So there exists a point R over here that we discussed earlier. There exists a point R such that, let's see here, we have PQR, that is, Q is between R and P, and RQ, distance from R to Q, is equal to the distance from Q to P. Excellent, and that is by the ruler postulate. So let's add that point R in. We already have it drawn. Let's label it. So we have this set up. Now what we want to do is we want to recognize that we have these distances are equal. So let's see. the notes that I have actually show this as a result of looking at congruent triangles. So we may go ahead and take a look at that direction. But I believe that we also have a theorem that states that O is on the perpendicular bisector if and only if it's the same distance away from the endpoints. So we could consider that one as well, shortening this proof, because we would immediately have that OR and OP are the same distance. But I don't have that in front of me as to what theorem that is. So we're going to take a slightly different approach for now and use the fact that, let's see here, angle RQO and angle PQO are congruent, right? Because it's a perpendicular bisector. So those are congruent by the definition of a perpendicular. I know it's not working out perfectly on this example, but keep in mind that it's nice to have these lined up separately from one another, what we want to say and its justification. Be nice if these were all lined up. All right, so of course QO is congruent to QO, that is the line segment QO. And that is by the reflexive property of congruence. And that gives us that RQ is equal to PQ, angle RQO is equal to angle PQO, and side QO is equal to side QO. So by side angle side, we have that this triangle and that triangle are congruent, and that RO is equal to PO. So we have, let's see, triangle RQO is congruent to triangle PQO by side angle side. So RQ is equal to QP. That's given right here in line 4. So that's our first side. Angle is equal to angle, or congruent to, that's given in line 5. And then this side is congruent to itself, given in line 6, which allows us to conclude that RQ, or that RO, is congruent to PO. In particular, their distances are equal to one another. And that's by the definition of congruent triangles. So with that, we have that R is on the circle centered at O, right? R is on the circle centered at O with radius OP or PO. And this is by the definition of a circle, right? Because the distance is the same as the distance from O to P, so it must be on the circle. But our assumption was that T is a tangent line, and since it's tangent at P, then R is not on the circle. And that is by the definition of a tangent line. Of course, this produces a contradiction because it can't both be on and not on. The contradiction is lines 9 and 10. So we conclude that this thing is not true. So we have that line segment OP is not perpendicular to T. That is, line segment OP is perpendicular to T. And that's by lines 2 and 11. So here's 11, here's 2. And that's it. Excellent. So we have the tangent radius theorem. If we have OP, right, OP is perpendicular to the tangent line T, where T is tangent to the circle at point P. All right. All right, the last thing that I'd like to take a look at for this video is the congruent tangent segments theorem. So we have if lines L and M intersect at A and are both tangent to a circle at P and Q respectively, then we have AP is equal to AQ. Kind of wordy here, so let's take a look at what we're trying to say. So if we have a circle and a point A, we have two lines L and M that are tangent to the circle and both pass through A, right? They intersect at A. So we're looking at the line that is tangent to the circle, passes through A, tangent to the circle, passes through A. My A was a little bit off, so let's just move that. That looks good. So we have, let's call it line L and line M. And we said that L is tangent to the circle at P. L, so P is over here. And M is tangent to the circle at Q. Then we have the distance from A to P is equal to the distance from A to Q, right? Those two things are congruent to one another. They have the equal distance. All right, and the proof of this is an exercise. So keep this image in mind. Maybe has something to do with chords. Honestly, I don't know. I haven't thought about it. So that's one way to go, and then to think about what a diameter might look like. I don't know. I'm just spitballing right now, right? Giving an example of what it looks like to think about a proof. So that's it, though. That's it for this section. So, or not for this section, but for this video, we still have quite a bit to talk about. Arcs of a circle. So in the next video, we're going to take a look at a collection of definitions. And then we'll take a look at another video with a theorem and a couple more definitions. And then we'll have a very brief video which follows up with a computer exploration for you to work on. So it's a long section. So thank you for your time and your attention. For now, I will see you guys later. Look forward to the next videos being posted shortly.